Having learned about analytic functions and the types of singularities, now it is time to turn to integration on complex plane. So, we will be considering integrals on complex plane that involve analytic functions and functions having various types of singularities. Most often we will be confined to functions having poles on the complex plane due to constraints on time. However, if time permits, we will also see a couple of examples of integrals involving functions with branch cuts and so on in the tutorials. So, let us look at integrals on a complex plane, starting with integrals involving analytic functions. Let us consider an analytic function f of z, that is analytic, and let f of z be analytic in a particular region, a domain of the complex plane which we term D, and consider an integral of f of z between 2 points, let us term those points A and B, both lie inside that domain D where f of z is analytic. So, by saying that f of z is analytic in D, we should keep in mind that we are referring to the fact that f of z obeys Cauchy-Riemann conditions inside the domain D, as well as the derivatives, all the derivatives of f of z are continuous and finite in D. Now, if I consider a line integral from A to B, the question arises as to which line should I take to do this integral. There are several lines that you can consider, starting from A and ending at B. That is one curve which takes me from A to B. This is another, and I could find in fact infinite number of curves, all of which lying inside D, to go from A to reach B. Okay. So, let us try and let us try to learn one important aspect of these distinct curves along which I could integrate f of z as I go from A to B. To do that, let us consider in fact two line integrals to begin with, going from A to B like that, not of any particular shape, but only by ensuring that both the lines that we consider remain inside the domain D where f of z is analytic. Let us consider these line integrals in a particular order. Let us first consider the integral from A to B, and then also consider an integral from b to a. We are doing this with a purpose which will become clear as soon as we are finished with this exercise. So, if I consider integrals from a to b and from b back to a of f of z, overall I could term this integral as a closed integral indicated with a circle over the integration symbol, integral over a closed curve of f of z. Let us write this integral in detail by choosing a specific form of f of z. Well, not specific, but general form of f of z taken as u plus I v, where u and v are the real and imaginary parts of f of z, and z being x plus I y. Now, so if z is x plus I y, then the measure dz over which we integrate, the measure of integration can be written as dx plus I dy in terms of the real and imaginary Cartesian variables x and y. Using this form back in here, we could write this closed integral, which no longer has limits. It is an integral that starts from a and comes back to a, as u plus I v into dx plus I dy. Separating this into two pieces, one a real integral and another an imaginary integral, we get the real part of this to be u dx minus v dy plus I into v dx integral over I into integral over v dx plus u dy we could now see that we could write this integral into two pieces, one a real piece and another an imaginary piece. Remember, both these are again closed integrals, integrals over a closed loop. Now, having the real part of, if you look at the real part of this integral, you could see that integral is u dx minus v dy. You can think of such an integral as a integral of a vector function a over the same closed loop expressed in this form, where a is a vector function of x and y, such that its x component is u and its y component is minus v. remember dr, the line element is dx x hat plus dy y hat. With this choice of A, you could easily check that A dot dr gives us this quantity u dx minus v dy. Now, if I have a vector integral of a line integral, a closed line integral of this form, we know that Stokes' theorem allows us to write that as a surface integral over a surface enclosed by this particular closed loop, which let me term from now onwards C. That closed loop will henceforth be called C. So, if S is the area that is enclosed within that closed loop C, so that area within that loop is what I would call SC. I could write the line integral over such a closed loop of A dot dr, A dr as curl of A dot ds, a surface integral of the curl of A over this closed surface, which is enclosed inside that loop C. And it is easy for us to see what curl of A will be in this context. Curl of A gives us del by del x of A y, the y component of A, which in our case is minus v, minus del by del y of the x component of A, which in our case is u, and since we are on a two-dimensional plane, that is the only component of curl of A that we have. Or you can also say that this component is the z component, if you wish, if you think of this, think of us as working in 3 dimension. So, substituting this there, we can find that the particular line integral along a closed loop that we are interested in evaluating becomes this quantity, which itself is given in this form. But now, let us get back to the function that we are considering and the particular loop that we are looking at. The loop over which we integrate this function is considered inside a domain D, where this function f of z is completely analytic. If it is analytic, then certainly it has to satisfy the Cauchy-Riemann conditions. In the domain D. Now, if that is the case, then the real and imaginary parts of f of z obeys del u by del x equal to del v by del y, which is the first of the Cauchy-Riemann conditions, and del u by del y equals minus del v by del x. Okay, so if del u by del y is equal to minus del v by del x, then I could use this expression for del u by del y here and see that the curl of A vanishes. Not only that it vanishes for all points inside D. In particular, since we are interested in points inside points on the surface SC, which is lying inside the closed loop C, even there the curl vanishes, and that tells us that A dot dr, the closed line integral of A over this curve C, closed curve C, must be 0. Well, strictly speaking, I have looked at only the real part of the integral f of z dz over the closed loop C. I should now also look at the imaginary part of the same, which involves another real integral. If I look at the coefficient of I, the integral that we see is again a closed integral over the same curve C, same closed curve C of another set of real functions, and that we can easily again show vanish due to Cauchy-Riemann conditions, especially the Cauchy-Riemann conditions given by del u by del x equal to del v by del y. So, let us complete that exercise by looking at the imaginary part of that integral as well, which is of the form v dx plus u dy. Again, it is easy to observe that I could write this as a closed line integral of b, vector b, of another vector function b, where b takes the form v x hat plus u y hat, and dr taking the already mentioned form of dx x hat plus dy y hat. Again, observing that this can be written as curl of B over the same closed surface SC enclosed by the closed line C. Now, computing curl of B, we get del by del x of the y component of B, which is u, minus del by del y of the x component of B, which is v. Now, looking back at the first of the Cauchy-Riemann conditions, we immediately recognize that this del v by del y is equal to del u by del x, and hence the curl of B vanishes as well, which tells us that even the imaginary part of the integral f of z over a closed loop C vanishes, which tells us that this whole integral is 0. Now, this tells us that a closed line integral of an analytic function of f of z over a contour C, which is considered in a region where f of z is analytic, has to be 0. Now, this helps us to answer the question that we considered earlier, which was whether a line integral done from A to B over a particular contour will differ from a line integral done over a particular line would differ from the line integral done through another curve A to B. The answer can be now found by writing this closed line integral as a line integral from A to B over, let us say, C1. This part of this closed line, which I will separately call C1 now. The line integral itself was called C, closed line integral itself was called C. The part which takes me from A to B is from now onwards called C1. Plus that line integral partly consists of C1 in addition to the part that takes it from B to A through another line which I will call C2. F of z dz. The result that we obtain tells us that this has to be 0. Now, since an integral from B to A can be written also as negative of integral from A to B, it is done in a reverse order. We can now see that this integral which was done over line C1 and this one done over line C2 in reverse direction, they added up to give me 0. Since this can be written in as minus of an integral from A to B f of dz, f dz. Now, we get the result that this has to be equal to 0. Remember that this integral was done over a line which we called C1, while this one was done through another line C2. And since the difference between them is 0, it is clear that both line integrals will give us the same answer, which tells us that if whenever I consider analytic functions, their integrals from one point A to another point B should give us the same result irrespective of which path you choose to do that integral. Okay. So, we can say that f of z dz, integral f of z dz is from A to B is path independent. And it is path independent precisely due to the analytic property of the function f of z. So, this is the nice property of analytic function, that their integrals are path independent.